Dear students, I am Mahesh Javalkar from Marathamandal Polytechnic, and today I will be introducing a new thyristor family component which is called as IGBT, insulated gate bipolar transistor. Okay, so first we'll see the outline of this. In this presentation, I am going to tell you a definition of IGBT, symbol of IGBT, features of IGBT, other names of IGBT, structure of IGBT, working of IGBT, types of IGBT, output characteristics of our IGBT, transfer characteristics of IGBT, and applications of IGBT. Okay, so let's start with the definition of IGBT. So here you can see IGBT means insulated gate bipolar transistor. Insulated gate bipolar transistor. So insulated gate is a word which you have heard in MOSFET, and bipolar transistor is a word which you have heard in BJT. So it is a combination of features of MOSFET and BJT. Okay. So IGBT means insulated gate bipolar transistor. It is a three-terminal semiconductor switching device that can be used for fast switching with high efficiency in many types of electronic applications. Okay, so here we can see that it is a three-terminal device. Okay, and the terminals here will be emitter, collector, and gate. Okay, so emitter and a collector are the terminals which are resembled to BJT, and gate is a control terminal which resembles to MOSFET. So it is having a combination of the best features of MOSFET and BJT, okay, which is called as IGBT. Then if you see the symbol of IGBT, okay, so you can see there you are having gate, collector, and emitter. Okay, so it is a fusion. So here you can see the gate. So here you can see the gate, which is like your FET. So here you can see gate, which is the control terminal. This is the control terminal. This is the control terminal. And here you are having collector, and here you are having emitter. The current is going to flow from collector to emitter. Okay, so these are your BJT like terminals, collector and emitter, and gate is like your MOSFET terminals. Okay, so if you see the explanation here, IGBT is a fusion between a BJT and MOSFET. The symbol of the IGBT also represents the same. The input side represents a MOSFET with a gate terminal. Okay, MOSFET with a gate terminal. So it is an insulated gate. And the output side represents a BJT with a collector and emitter. Okay, the collector and emitter are the conduction terminals, and the gate is the control terminal with which the switching operation is controlled. Okay, so it is controlled by the insulated gate only, as we do the control in MOSFET. Okay, and the current is going to flow from collector to emitter. Clear? Then we'll go to the next point. Now here if you see, MOSFET plus BJT is equal to IGBT. This is a general combination what we can show. The best feature of MOSFET and the best feature of BJT, the best advantages of these are combined to get the IGBT. Okay, so the three terminals of IGBT are gate, collector, and emitter. Okay, then we'll see the features of IGBT. As I've told you, the best features of IGBT are the best feature of MOSFET, which is your high input impedance, and the best feature of BJT, which is low on-state power loss. Okay, so high input impedance is taken from MOSFET, and low on-state power loss is taken from BJT, and both these advantages, okay, are put into IGBT. So IGBT have high input impedance, low on-state power, so it is having a fast switching time, okay, and its efficiency is more. So it is having the best qualities from BJT and MOSFET, best features from BJT and MOSFET, which is combined in the IGBT, that is insulated gate bipolar transistor. So you have other names of IGBT also. IGBT also can be called as metal oxide semiconductor insulated gate transistor, MOS IGT, or it can be also called as gain modulated field effect transistor, GEMFET. It can be also called as a conductively modulated field effect transistor, COMFET, or it can be called as insulated gate transistor, in short, IGT. Okay, so it is IGBT, which is insulated gate bipolar transistor. Clear? Then if you see the structure here, if you see the structure of IGBT, you can see that here you are having metallic conducting. So this is full metal. This is full metal here. This is the metal which is directly connected to a emitter point, and that is directly connected to the semiconductor point here. This is N plus, this is P, this is N plus. Okay. So even here you can see the same thing. This is the metal, whatever is there, and that is connected to emitter, and that emitter is connected to N plus P. This is your P type of terminal, and this is your N plus. Okay. So here, this both emitter are connected together. These both emitter are connected together, and a common emitter line will be called here. So this can be called as common emitter line. Okay, so this is a common emitter. So here, this emitter is directly with a metal connected to the semiconductor. Okay, so that is what about emitter, what we can see. If you see the gate, this is the gate metal, this is the gate metal. Okay, now in this gate metal here you are having silicon dioxide. So this is your silicon dioxide, SiO2. This is silicon dioxide, SiO2. So this is silicon dioxide. So here we have shown that this is SiO2. Okay, so silicon dioxide. So this is your insulator. So here the metal is there. This is the metal part. This is the insulation part. And here you are having semiconductor part. Okay, so this is metal oxide semiconductor. So here you are having that feature of MOSFET. Here you are having feature of MOSFET. This is metal. Okay, this is oxide, and this is semiconductor. Okay, so MOSFET feature will be there. Okay, and now in this structure you can see this N plus buffer regions, N plus, N plus. Here you can see N plus, here you can see N plus, here you can see N plus, and here you can see N plus. Then you are having a P type of region here, P type of region here, P type of region here. Then you are having N minus region here, and then you are having P plus region here. So here down you can see the complete is metal. The complete structure is having a metallic contact, and on that metallic contact you are having P plus region, and that metallic contact is called as collector. This is your collector. Okay. Now that P plus and this N minus will form a junction J1. So here you can see your junction J1. So here is your junction J1, which is formed between these two. And then between this N minus and this P, between these two you can form junction J2. And between this P and the buffer region N plus, you can have this junction J3. Okay, so here you can have this junction J3. Okay, so like this you can have junction J1, J2, J3. Now near the collector, if you see, okay, near the collector, if you see, the collector is connected to the first P plus region, to the first P plus region, which is called as injection layer. Okay. Then upon that you have your N minus region, which is called as drift region. Upon that you have your P region, which is called as body region. Okay. This is called as body region. Okay. And here you are having your SiO2 layer. On top you are having your SiO2 layer. This is your SiO2 layer. Okay. Now this is the structure of your IGBT, where it is having three terminals. One is called as gate, which is insulated gate. Then you are having two parts of emitter, which are commonly connected and called as emitter. And then at the down, you are having collector region. Okay, so this is the structure of your IGBT. Now, in this structure, you can form two transistors as it is shown Q1 and Q2. Okay, so two transistors are shown here. One is your Q1 transistor, and the other one is your Q2 transistor. Okay, so here, if you see, you can have your Q1 transistor here, and you can have your Q2 transistor here. Okay, so this is nothing but NPN, and this is nothing but your PNP. Okay, so NPN and PNP, two transistors you can form, and you can have an insulated gate. So the input here will be an insulated gate. So here you can see the input is an insulated gate, which will give you high input impedance, and the output will be taken from the transistors, which will give you low output impedance. Okay, so here the features of MOSFET and BJT are combined in the IGBT. Okay, now, to understand the working of IGBT, the note we can read first. Consider a voltage source VG which is connected positively to the gate terminal with respect to the emitter. Consider the other voltage source VCC are connected across the emitter and collector. Okay, where the collector is kept positive with respect to the emitter. Due to the voltage source VCC, junction J1 will be forward bias, whereas the junction J2 will be reverse biased. Since J2 is in reverse bias, there will be no any current flow inside the IGBT from collector to emitter. Okay. Now this we can show with this figure over here. So here you are having the structural diagram of your IGBT, and in this structural diagram you can see that. Okay, so here you can see that your emitter is divided into two parts, which you can connect them as a common emitter. Okay, and then you can take this gate as a output gate here. So this common emitter, now gate should be positively connected. Okay, so gate should be positively connected. So emitter will be negative, positive, negative, positive. So this positive will go to the gate. So this is positive, this is negative, this is voltage VG. Okay, this is voltage VG. Okay, now this is what is the connection between gate and emitter. Gate is positive with respect to emitter. Similarly, collector will be, okay, similarly, if you see this connection for the collector, collector will be positive with respect to emitter. So here it is negative, positive, negative, positive. So this positive should go to the collector region. Okay, so here you can see the collector region. Now here this voltage will be called as VCC. This voltage will be called as VCC. This is plus, this is minus. Okay, so here you can have a minus line. So this is plus, this is minus. So this is VCC. Now with this connection, if you see, now here a collector is given to a positive terminal. So here you can see this positive terminal. This positive is given to the collector. Okay, so here you are giving positive to the collector, and collector is connected to P plus region. Okay, and this negative is connected to this N minus region. That means junction J1 will be forward biased. Junction J1 will be forward biased. Okay. Similarly, with the same voltage polarities, if you see, if this N is connected to positive here down and the top P is connected to negative there, then junction J2 will be a reverse bias. Okay. Now, because junction J2 is reverse bias, there is no flow of a current here. There will be no current flowing from collector to emitter. Okay. Now, if you apply a voltage VG, now if you apply a voltage VG here to the gate, okay, so here you are applying a voltage VG, which is positive polarity here. Okay, then here you will be having negative ions in the oxide layer. Okay, and here you will be having positive ions here. Okay, and because of this, in this P region, you will induce negative charges. In this P region, you will be inducing negative charges. So negative charges will be induced in this P region. Now, this negative charges will be such that they will form a channel. They will form a channel between collector and emitter. They will see that the second junction goes into breakdown, and there is a current flow from transistor from the collector to the emitter, from here to the emitter, or from here to the emitter. There will be a current flow. So as you increase this voltage VGS, as you increase this voltage VGS, okay, VG. So this current which is going from collector to emitter will go on increasing. So that is the control voltage what you are giving at the gate, and this is how the current from collector to emitter will go on increasing. So this was the explanation of working of the structure of IGBT. So next we will see the note on that. Initially, consider that there is no voltage applied to the gate terminal. At this stage, IGBT will be in a non-conductive state. Now, if we increase the applied gate voltage due to the capacitance effect on the SiO2 layer, as we have seen in MOSFET, also insulated gate, the negative ions will get accumulated on the upper side of the layer and the positive ions will get accumulated on the lower side of the SiO2 layer. This will cause insertion of negative charge carriers in the P region. Higher the applied voltage Vg, greater the insertion of negatively charged carriers. So if you increase the voltage Vg, the negative charge carriers in the P region down will go on increasing. This will lead to a formation of channel between the J2 junction, which allows the flow of current. Okay, so that junction was actually reverse bias. Now it is allowing, it will go into one type of breakdown and it will allow the flow of current from collector to emitter. When the applied gate voltage Vg increases, the amount of current flow from the collector to emitter also increases. This is what is the basic working when you see the structure of IGBT and if you explain the structure of IGBT working. Okay. Then next we will see. Now here, if you see equivalent model, okay. Now the structure of IGBT shows you that there are junctions J1, J2, J3. There is a transistor Q1, Q2 formed, and similarly there is an insulated gate. Now that full thing you can show in a equivalent circuit. So here you can show a insulated gate. So this is what is a insulated gate, and the same transistor Q1 which was here. So this transistor Q1 is shown here. Okay, and this transistor Q2 is shown here. Okay, so here you can see insulated gate which will give a high input impedance, and the output is of transistor which will give you low impedance. And now here you can see this Q1 and Q1 and Q2 are in a latch. This is a latch, same like your SCR latching. Okay, SCR latching, or it's called as thyristor latching. So once you give the gate pulse here, once you give the gate pulse here, this both transistor will go into on condition, and the collector current of one will be the base current of other, and that will remain in the latch, and the IGBT will be in on condition even if the gate loses its control. Okay, now in that case it is somewhat like your SCR working. Okay, so one side we have shown the structure of IGBT, and the other side I have shown the equivalent model of IGBT. Okay, then with that full thing we can conclude that the two transistor back-to-back connection forms a parasitic thyristor, a parasitic SCR, as shown in the figure of equivalent circuit. This N-channel IGBT turns on when the collector is at positive potential with respect to emitter, and gate also at sufficient positive potential, that is more than the threshold voltage VGET with respect to the emitter. This condition leads to the formation of an inversion layer just below the gate, because all the negative charges will be formed in the p-type layer. So it is called the inversion layer, leading to a channel formation, and a current begins to flow from collector to emitter. This is what we can conclude on the working of IGBT. Okay. Then we'll go to see what are the types of IGBT. Okay. Now in Types of IGBT. IGBT are classified as two types based on the N plus buffer layer. So initially below the emitter, we have seen that N plus buffer layer. The IGBTs that are having the N plus buffer layer are, are called as punch through IGBT, PT IGBT. And the IGBTs that does not have the N plus buffer layer are called as non-punch through IGBT, NPT IGBT. Okay, so if the buffer layer is present, if that N plus layer is present, then it is called as punch through IGBT. If that N plus layer is absent, then it is called as non-punch through IGBT. Okay, so based on the characteristics of NPT, that is non-punch through IGBT, and PT IGBT, that is punch through IGBT, are named as symmetrical and non-symmetrical IGBTs. The symmetrical IGBT are the ones that have equal forward and reverse breakdown voltage. The asymmetric IGBTs are the ones that have reverse breakdown voltage less than the forward breakdown voltage. The symmetrical IGBTs are mostly used in AC circuits, whereas asymmetrical IGBTs are mostly used in DC circuits because they don't need to support voltage in the reverse direction. Okay. Now this is the difference between your non-punch and your punch IGBTs. Okay. So then we'll go to see characteristics of IGBT. So the first characteristics what we see is the output characteristics of IGBT, which is same like your output or your drain characteristics of your MOSFET. Okay. So here you can see the symbol of IGBT, which is shown here. So here you see this is collector, this is your emitter, okay, and here you are having your gate. So this you can call it as gate here. So here you can have your gate here. This is your gate. Okay, so here you can see this is the gate. So this gate is connected to the VG voltage. Okay, so here positive gate is connected. So here you can see this is positive, which is connected to the gate, and negative is connected to the emitter. This is emitter. Okay, this is emitter. Similarly, a positive is connected to the collector and negative is connected to the emitter. Same what we have shown in the structural diagram. And that voltage will be called as VCC here. And the input voltage will be called as VG here. Okay, so here you can see VG. So here you can see VG and the output you can see VCC. Okay, so initially when the VCC voltage is minimum, there is some minimal voltage between emitter and collector, and if the applied voltage gate is 0, there will be no current flowing. So as you have seen in this graph over here, so you can see in this graph over here, there is no current flowing from 0. Okay, so here you can see there is no current flowing here, there is no current flowing. But as the gate voltage reaches the threshold voltage here, okay, threshold voltage, the current will start flowing. The current will start flowing. There will be a channel between your collector to emitter, okay, and there will be flow of current which will remain constant in the next time. Next, sometime it will remain constant and then it will go into saturation. Similarly, if you increase the gate voltage, the magnitude of the current between the collector and emitter will increase here. Similarly, again, if you increase the gate voltage, the magnitude will increase. It will remain to some constant value and then it goes into saturation. Similarly, again, if you increase the gate voltage, the magnitude of the current will increase and it will go to saturation after some time. Okay, so this collector current magnitude will increase as you increase the gate voltage. So here you can see here you are increasing, here you are increasing, here you are increasing, and here you are increasing. So here down you can see that VGE1, that is voltage, the first gate voltage is less than the second gate voltage, and then with the third gate voltage, and same with the fourth gate voltage. Okay, so this is your drain characteristics of IGBT. Okay, similarly you have one more characteristics which is called as transfer characteristics. These are same type of characteristics what we have seen in MOSFET. So if you see here, initially when the gate voltage is applied, initially when the gate voltage is applied, there is no current flowing till the gate voltage reaches the threshold voltage. Okay, so here if you see the gate voltage, which when it reaches the threshold voltage, So here initially there is no gate current here. Here there is no gate current. So there is no collector current. Now when the applied gate voltage reaches the threshold voltage, okay, so this is gate voltage, which is threshold voltage. At that time, the channel between the collector and emitter will form. The negative charges in the P layer will be inserted, and there will be a current flowing from collector to emitter. That is what will be increase in the collector current. So this will be your increase in collector current. Collector current is increasing. Collector current is increasing. So increase. So this is increasing because you are increasing gate voltage. Okay, the gate voltage is increasing. Okay, so the relation between input voltage gate and output collector current will give you the transfer characteristics of IGBT, which is same like your MOSFET. Okay, so these are the transfer characteristics of IGBT. So we have seen two types of characteristics. One was your drain characteristics or output characteristics or static characteristics, and the second one is the transfer characteristics. Then we'll go to see the applications for IGBT. IGBTs are used in various applications such as number one, AC and DC motor drives. Number two, unregulated power supplies, that is UPS. Number three, switch mode power supply, that is SMPS. Number four, hot traction motor control. Number five, induction heating. And number six, inverters. And many more applications are there where IGBTs are used. Okay. So if you have any a commercial type of IGBT which you have seen in the market, it can look like this. The example which is shown over here is 25N120 1200 volt fast IGBT power transistor, where you can see the three terminals. The three terminals will be your gate, emitter, and collector over here. So one, two, and three terminals you can see here. And these terminals you can connect to the appropriate connections when you are putting it in the circuit. Okay. Thank you, students. This was the introduction of IGBT, and IGBT also is an important component in your thyristor family. So, whenever we study power electronics, the first important will be SCR, then the second will be diac, and triac will be the third, and fourth will be IGBT, what you see in the thyristor family. Okay, thank you very much.